A metal oxide varistor, MOV, is the bodyguard of an electronic circuit. Its job is to sit quietly and do nothing until a dangerous voltage spike, like a lightning strike or a power surge, happens, at which point it jumps into action to protect your devices. Here is exactly how it works at both a microscopic level and a circuit level. How it works inside the microscopic level. An MOV isn't just a piece of wire. It's a ceramic mass made of zinc oxide, ZNO, grains, mixed with other metal oxides like cobalt or manganese. Grain boundaries. Imagine the inside of the MOV as a bunch of tiny conductive grains of zinc oxide. Between these grains are boundaries that act like tiny insulating barriers. The breakdown. Under normal voltage, electrons don't have enough energy to jump over these barriers. But when a high voltage surge hits, the electrical field becomes strong enough to punch through these barriers. A process called tunneling or avalanche breakdown. Conduction. Suddenly, all those tiny barriers disappear, and the entire ceramic disc becomes highly conductive, allowing thousands of amps to flow through it for a fraction of a second. You can think of the process as creating a controlled chemical sandwich around every single microscopic grain of zinc. Number 1. The sintering process. The boundaries aren't created by hand, but through a high-temperature process called sintering. The mix. Engineers start with a powder of zinc oxide, ZNO grains, the balls. To this they add small amounts of dopants, other metal oxides like bismuth, antimony, or manganese. The press. This powder mix is pressed into the familiar disc shape under high pressure. The heat. The disc is baked in a kiln at temperatures between 1000 degrees Celsius and 1400 degrees Celsius. Number 2. Forming the grain boundaries. During the baking process, the zinc oxide grains grow into large crystalline grains, but the bismuth oxide acts differently. The liquid layer. At high temperatures, the bismuth and other oxides melt and flow around the solid zinc grains. The coating. As the MOV cools, this melted mixture hardens into a thin, insulating layer that completely surrounds every single zinc grain. The barrier. This layer is only a few molecules thick, but it creates what is called a Schottky barrier. How the balls behave. Imagine a jar filled with marbles, the zinc grains, and then you pour honey, the bismuth mix, into the jar so it coats every marble. Under low voltage, each marble is separated by a thin film of honey. Since the honey is an insulator, the electricity can't flow from one marble to the next. Under high voltage, when the electrical pressure, voltage, gets high enough, it triggers a breakdown in the honey. The electrons gain enough energy to tunnel through the honey layer, turning the entire jar into a conductor almost instantly. Why use balls instead of one solid block? By using millions of tiny grains, the MOV creates a massive network of these barriers. This allows the component to handle huge amounts of power, because the energy is spread out across millions of tiny junctions rather than hitting just one spot. It makes the device much more durable and reliable. The circuit role, the emergency exit. In a standard circuit, an MOV is connected in parallel across the power lines. Under normal voltage, under normal conditions, the MOV has extremely high resistance, millions of ohms. It acts like an open switch or a wall. No electricity flows through it, and the power goes straight to your device. Voltage spike. If the voltage suddenly jumps above a certain threshold, called the clamping voltage, the MOV's resistance instantly drops to almost zero. It becomes a short circuit for the surge, diverting the extra energy away from your sensitive electronics and safely into the ground or neutral line. A DC MOV works on the exact same physical principles as an AC MOV, using those zinc oxide balls and grain boundaries to block or shunt current. But the application and stress levels are very different. Think of it this way. In AC, the voltage is constantly passing through zero, giving the MOV a tiny break 100 or 120 times a second. In DC, the pressure is constant. The core difference, constant stress. Because DC voltage is a steady push, the MOV has to be much more precisely rated. Leakage current. In a DC circuit, If the MOV's clamping voltage is too close to the operating voltage, a tiny bit of electricity will constantly leak through the grain boundaries. This creates heat. Over time, this heat can destroy the MOV, thermal runaway. The turn-off problem. In AC, once a surge passes, the voltage naturally hits zero, which helps the MOV reset and stop conducting. In DC, there is no zero cross. If the MOV starts conducting, shunting, and the DC power source is strong enough, the MOV might stay on and keep drawing current until it burns up. How DC MOVs are specified. When you look for a DC MOV, you'll notice the ratings are different. An MOV rated for 130 volts AC might only be rated for 170 volts DC. The DC hybrid approach. Because DC power is so much harder to stop once it starts flowing through a varistor, engineers often don't use the MOV alone. They use a hybrid protection circuit. One gas discharge tube, GDT, often placed in series with the MOV. The GDT acts like a physical air gap that blocks all leakage current. 2. The MOV handles the actual clamping of the voltage. Can you use an AC MOV for DC? Yes, but with a warning. You must look at the datasheet for the maximum DC voltage, V sub DC. If you use an AC-rated MOV on a DC circuit and the voltage is even slightly too high, the MOV will slowly cook itself. The rule of thumb, for DC, always choose an MOV where the V sub DC rating is at least 25% higher than your steady-state DC voltage to account for fluctuations and heat.